Hello, hello. Welcome again on 34th Wro.cpp meetup. This is the first meetup this year, so I'm happy that we managed to finally organize something starting from first month. So I'm happy to keep it rolling. So we are going to continue the goal, which is make you guys successful as a C++ specialist. Our main high-level goal. And I have presented it last year the kind of the roadmap. So today we are going to cover some parallel processing, which I think will cover multi-threaded and multi-process topics as well. If you have any other topics that you would like to have covered during those meetups, please do not hesitate to use the forms and let us know what you would like to have here. I have a robotic voice. Not good. Not good. Grzegorz, do you hear me as well as a robotic?
Yes, it's a little bit kind of
no.
like okay, there is some echo. Oh, you drank too much.
I should stop drinking then. Let me try something else then.
I will turn off maybe echo cancellation. How is now? Better?
It's a lot better.
Okay, so thank you, August. Okay, thanks to cooperation with other meetups or other C++ events, we get some promotional code for getting still now. Oh my God. Okay, I will check that in a second. Luckily, I am not the presenter now, like today. Okay, so I will be short now. So we have like promotional code. So Wro.cpp 2025 is the code. You will get a 50% discount for getting the C++ online 2025. So just use it if you are going to watch it. So we are on our social media channels. So if you are not following us there, just go there and please follow us, like us, and share the good word about us to others, because that is how we can grow and how we can organize those meetings. There is a web page on the GitHub. I confess that it's already not up to date, so I will need to work on that. And also, if you are willing to support me with that, and you know GitHub, and you know something regarding how to write the content, just give me some shout and contact me, and I will love to receive some help with that. You can support us also on the Patreon, so feel free to donate us. And we have one Platinum patron, which is Adam Badura. I promised him to promote him here, so I'm doing that. And somehow I lost my slide where I was talking about agenda. Yes, exactly. So sorry, the microphone thing made me lost that slide. So today is Grzegorz Wojciechowski, who will be presenting parallel processing topic. I assume it will be 60 minutes, but Grzegorz, don't be limited to that. If you need more, just talk. Talk as much as you need it. So okay, so now I will stop my talk. I will turn on the presentation. From Grzegorz. So guys, I will be on the backstage, of course. I will be responsible for switching some screens. So if something will go wrong with Grzegorz presentation, it will be my fault. And if you will have any questions, do not hesitate to write it on the YouTube. I will be forwarding them to Grzegorz. Okay, Grzegorz, the stage is yours. Have an awesome presentation.
Hello, and thank you for taking all the blame for the crashes of the application. So this will be helpful. But in reality, the topic of the parallel processing is interesting for many people. And talking with my friends working in the professional companies, there is a lot of people that think that they know about the parallel processing, they understand it, they know how to do stuff, but in reality, very often it's misunderstood the benefits and just how helpful the parallel processing is. And to talk a little bit why I'm talking about it is like I'm programming for 20 years already. I started when I was even more, 25, when I was 12. And my first work was in kind of indie times when the indie was still a group of the people that don't get paid and work on projects in the internet. And I was member of one of such a group for I think 2 or 3 years. But first big, like the proper work for me was when I joined Techland after the internship. I worked there for, if I could remember, 4 years. And after 4 years, I was part of the engine team, was working on moving from DirectX 9 to DirectX 10, 11. I was in the time when Xbox One and PS4 was introduced to the as the new platforms. I was helping with moving the technology to these platforms. Then I moved to Ubisoft Montreal, where I worked for 2 years, and they are help with the Far Cry to do similar transformation to move to Xbox One and PlayStation 4. After that, I moved to England to the Sumo Digital when I was helping with moving Forza Horizon to DirectX 12. And after 1.5 years, I landed the job in the Unity, which was unplanned, but I joined the core kernel team, so the team that taking care of the lowest possible things, like the memory, containers, multithreading, profiler, and spent there another 7 years. Last year, I left Unity and joined Huawei. And finally, over all this time, from the more than 20 years, I developing my own technology, which we'll be talking about. And this technology is utilizing a lot of the multi-threading systems that I will be talking about. So I think I have some credentials to at least talk about the topic. It's like don't know everything because nobody know everything, but a lot of stuff is just coming from the experience and stuff that I really needed to do when I was learning these things. So the first thing that we need to understand what is the parallel processing, because there is a lot of misunderstanding what it is. This is the 3 comments that I took from the Stack Overflow. First is in computer, parallel processing is the processing of program instruction by dividing them among multiple processors with an objective of running a program in less time. In the earliest computers, only one program ran at a time. Parallel processing, a processing technique in which multiple processors or multiple processing cores in a single computer works together to complete one job more quickly. And parallel processing is the execution of one job by dividing it across different computer processors. And what is interesting, there are multiple topics here touched that dividing between the multiple process, dividing work in less time. This is the kind of the interesting thing is what is less time processing, even questions like that. So to understand what we really want to talk about the parallel processing, we need to know what it is. So I asked Google for it and got simple answer. Parallel processing, a mode of operation in which a process is split into parts, which are executed seamlessly on different processors attached to the same computer. So as we see, there is no talking about the performance. There is no talking about almost anything. It's just one process that is split into parts that running at the same time, at the same computer. Which is interesting definition, because I would still thought that processing on multiple computers should work. And also what is here about the parallel processing on mega computers. But this is not something to discuss. So let's think about it, how we can do it. The simplest way of processing multiple things is simple instruction, multiple data, so-called SIMD. This is this is one of the earliest optimization, where its target was to process faster. So process, for example, 4 things at the same time. And as we can see, we have 4 data which contain 4 different values. We're calling one operation, which then doing this operation on all the values at the same time. This is very efficient, but also very hard to optimize. So in my personal experience, only some parts of the code really we are able to simplify, like purposely. And in the current times, when the vector optimization of the compiler is already doing that for us, it's not so optimal as we could do, but it's doing it. It's kind of moving more and more to this bizarre part of the code, of the coding that only few doing. And one of the reasons is because it's hard to do. It's hard to optimize it. It's really giving big benefits within the tight loops. The another, there is difference between the SIMD operation across different architecture. So ARM have different commands than x86 and x86 64. Another problem is these command sets are not always compatible. I've seen some libraries that allowing you to use one syntax for both of them, but in some cases, some commands from the x64, x86, 64 are replaced by multiple commands on the ARM. So it's possible to do. I know that some people finding a lot of fun of it. It's have its place for very tight algorithms, but it's not very general, and it's hard to kind of optimize for it. The second way of fixing stuff is multithreading. If we have in current era where the computers are having multiple cores, multiple processors, it makes perfect sense to run things at the same time. In some ways, operating system already taking care of that, but we would like to utilize it in single application. And the simple way to do that is just to start the thread, do some work, wait for it to finish, and then the processing. It's a very efficient way for some task. As we can see, here are 2 ways of doing that. One with the STT and one with the boost. How it looks in the execution time on the main thread with scheduling the threads with the task. There is small portion of the initialization which is not displayed here. There is overhead of spawning the thread. After that, there is execution of the task. And finally, there is the termination of the thread, which also is some overhead for shutting down the threads. Finally, in the meantime, we can see that I displayed that main thread waiting, and the red is waiting, is divided in between, because when one join end, we have some processing, which allowing us to move to the another join, which we're waiting for another thread. Which, as we can see, leave us with the main thread inactive, which in this case wouldn't be such a big problem, but we may want to fix it. And the simplest solution is not to wait only for the jobs, but also doing something on the main thread. So we're doing the modification of the code here, where we remove the last thread, and executing the task directly on the main thread, which kind of resolved the problem of the waiting and in theory everything working how it should be. Except that we cannot assume that the task will really execute like that. What if the file is a lot smaller and it will start executing differently? Then what will be happening is we have, once again, we're starting the task one, we start processing, we utilize some of the waiting, and in practice, we're still waiting and losing time on some threads. Depending on the configuration, this can be problematic one if we assume the thread to some other cores, which potentially we could use. So with the simple multi-threading, the problem is hard to balance workload in parallel processing. We don't know how long the work will take. If we know we are in the gold spot, we know that every task is more or less the same, it's perfect. But when we, depending on external factors, which we're processing some files, we can have in the games, for example, one can process texture 4K and one texture of 256, which make big difference. And also creating thread is cheap, but it's not free. This is the term that I found on the internet that somebody mentioned that, oh, it's cheap to spawn the thread. But I found that in some cases, in this case, it's talk about the macOS, it can take up to around 90 milliseconds to spawn the thread, which to some application, it's plenty of time. But to give the perspective, in the games, 33 milliseconds is one frame. This is all the time that you have to render, process physics, process everything. You cannot wait 90 milliseconds to spawn the thread to process something. In case of the more modern and faster game, you have 16 milliseconds, 60 FPS. And optimal for the VR, you have 8 milliseconds to do everything. You can, of course, do the trick and delay some things across multiple frames, but this is the time that we have. So 90 milliseconds giving us around here 11, 12 frames, which is a lot. While being in the Unity, I also seen interesting comparison of the time and understanding what is really the time kind of the computer. This is one of the seniors presented this at one of the presentation, and I spent some time just to search it. So if we imagine that one cycle of the CPU is just 1 second of our life, of the human life, and in the reality it's just 0.3 nanosecond, then accessing the L1 cache for the processor is 3 seconds. Accessing the main memory, where we skip the caches, is already 6 minutes. So it's like you're waiting 6 minutes to get some information. Accessing the hard drive, even SSD, is 2 to 6 days. This is how long in the perspective it is. And accessing the internet, it's already moving to the years. That's why I like this table, because it's giving to people that don't have full understanding what kind of time we're talking about. It's just showing them how much time we're spending on the things. And this is very visible in some usability application where things just taking forever to kind of process. Of course, time is money, money is time. It's better to write less efficient code to have, but have the code to ship it. But also, on another hand, it's getting worse and worse over the time when some low-level library is doing that. So when we already know that the scheduling is hard and the spawning the thread is problematic one, people figured out that it's nice to have some kind of task system, job system. How it is based, most of the companies that I work for were like writing their own software for that, so their own implementation. Some of them were not great, some of them were decent. One, you can find the implementation freely It's like there is a lot of them available. This is, for example, the task system running in the Naughty Dog in one of the Uncharted games. When they were porting they were doing the porting, and they were doing the parallelization with fibers. So they were creating their own job systems, and they had such a load of the task in the process. There is thousands of them, and they are very tight. What is interesting, a lot of them are also pre-configured for the hardware, so it's still happening, because in console very often we need to assign the specific thread, or in this case workers, to specific core, because if we don't have predictable execution of it. And it's getting worse on some platforms comparing to other, because for example on Xbox you have available all the cores except one of it can be shared with the operating system. So what happened, half of the core, half of the power can be consumed by some system operation. It can work perfectly fine, but then you're going into the system menu, starting some voice chat, and your game start to work worse. In others, you have only available half of the core all the time. This was the case at the beginning, where they just took away this half of the core and just did it. In the modern hardware, there is the issue of the slow cores. So this is like you have performance cores and you have the slow cores, which using less memory, less power, but they are slower. So for some tasks, it can be a problematic thing to kind of this. So there is a lot of these things to consider when scheduling and planning your execution. And sadly, on PC, you cannot really predict it. I already seen situation where code that worked perfectly fine on 8 cores, when moved to the machine with 4 cores and 8 threads, started to work very slow. And example implementation of the job, the one that kind of I have in my own engine, into my own technology, is the job system that allow you to schedule jobs, schedule them with the dependencies. And I have 2 special kind of the jobs. One of them is the trigger, and another one is the guard job. So in this case, we have some execution tree that we want. So we want to execute job 0 and 1. Job 2 need to be processed after the previous ones. Guard job, what it's doing is waiting for all the job that it's dependent on, and when it is, it just continue forward without doing anything. It's just kind of you waiting for all this job. It's for convenience, because otherwise, if after it there was 10 different jobs waiting for job 2, 3, and 4, we would need to pass always these 3 things as the dependency, which is hard to pass around, as you need to pass the array. And in this case, you're just passing this one job, guard job, and it's perfectly fine. And trigger is the mechanism which I added because of the external libraries, which is a problematic thing, because some external library don't allow you to hook up to your own job system, like the thread system. What they're doing, they spawn their own workers and process on these internal workers. And only thing that you know is when the job finish. And this trigger is the concept that you can manually trigger it, and it behaving like the job ended, and then it start to triggering all the other dependencies. And let's look into the code, how it looks. This will be the live show of the code that I have. Let's move to this one. And here we have it. This is the, we are there. So let's start with the job manager. So I have a concept of the group. Every group is scheduled based on the priority. So currently, I allow priority of the main thread, which is set as the priority more its affinity, so affinity priority, which will execute only on the main thread. This is to unifying the processing of the jobs across different threads. And in some cases, sadly, there are libraries that forcing you to use the main thread for processing. And you don't want, if something waiting for the main thread, you don't want to create some special code for it. That's why I included it here. Then there is the normal priority, which is the default priority for every task. Low priority, which happening less often. Not every, it will be picked later. So the first priority will be normal. There is also resource, which I have it separately because I encounter some problem between mixing the normal and if I put the resource loading inside the normal, I had some issue with the deadlocking because some of the tasks just process in different ways. So we pick up all the normal tasks, but you don't know if the normal task is the resource or not. And the resource need to always load. And this is important because whenever you're spawning the threads, initializing with the priority list. So what you're doing, you're creating the priority, which if we go here, is just the static vector. It's static vector for me is just the array with pre-allocated stuff. So you can push multiple kind of things. An example of the initialization like that, I have, for example, here, which is the job system. Yeah, I'm starting here the jobs, and I have the list of the worker groups and worker groups reserved, worker segment. It's not this one. Sorry. Let's see. It's over here. Yeah. So this is example of initialization of my job system. I taking the amount of the job system. I taking the amount. I have the low, medium, and high. This is the amount of the thread that I spawning. I have also auto, which automatically creating the amount of the thread based on the course that you have. And how it works, every thread has specified the priorities that it will process. So in the simple case, you will have the 4 workers threads, where one will first process normal and after that low. So I never processing any resources on it to not overwhelm it. On the second thread, I'm working on the normal, processing the resources, and then low. So it's processing the resources, but first it's picking any kind of the normal task. And finally, I'm putting 2 of them to resources, which are just loading the resources and processing of the resources, like models, texture, animation, any kind of the processing or loading that is needed there. And based on the configuration, I'm using different one. And when you spawn it, it's all in the job system. It looks like that. That there is the 4 job workers, which executing different kind of the works. I hook it up with the instrumentation. I think currently I have it broken because it shouldn't be everywhere, the water system, but it's executing different, like the different task and processing based on that. And then what we start to submitting the jobs. And the jobs, I have the different kind of it. Every job requiring the marker. And the marker is just for me the information about the name, color, and some instrumentation eventually. And the reason behind it is it's hard to debug the job system, and especially when you have very distributed application, like in my case. This is very good thing to always know what job executing, and this is passed all the way. And as you can see in the profiler, this is the superluminal. I'm hooking it up to see that something executing there. This is important because then it's easy to kind of see that in this case, sadly it's broken, but there should be cascade shadow maps here, and you right away know that everything below is just this. Then there is the submit with the dependencies. The use case of that, will be the job manager. Yeah. Let's start some tests. So we have it like that. This is the submitting without any dependencies. So we're just scheduling the job and doing the execution. And here you have we spawning the job A and then passing the job B. Starting the job B with the dependency on job A. So job B will never execute before job A. And in my case, I know that after talking with all gears, that is not the most optimal, but it's working perfectly fine for me. Is that the what happening when you committing stuff? The committing only adding the stuff that don't have the dependencies. So only if all the dependencies are met, this is only the moment when adding it to the queue, because otherwise, yeah. There are more optimal ways of doing that. And the reason behind why I choose this one is earlier I was using the always had the list of the jobs to execute. And the problem with that was that I spent so much time checking if the job is processed or not that it just was wasteful. So how I decided that I always pushing to the queue the stuff that's are ready. And whenever all the dependencies for the jobs are met, the last job that meeting the dependency will commit it to the queue. This way, it's from my test is pretty efficient. But of course, there are the research and papers for even more kind of elaborated method of queuing. Because in the end, a lot of the problem with the multi-threading is related to the scheduling. So we have this one. We cover this one. I have possibility to wait for the jobs, just to block and wait for the jobs to execute. From the interesting things, I'm able to turn it into the worker. So the reason behind it is like I had the cases where I just was not able, something is not in the queue and it was waiting for the processing. But I also built the system where I try to process the pending jobs, just in the way to collect the pending jobs and just process them. So you have the possibility to kind of, not wait for the. So if you have the dependency, you want to process all the dependencies up front. I'm using multiple queue. We'll get to that. We'll show that in a second in the processing. So existing job counts is not important, processing single job. And this is something that I'm using in the every kind of worker. So what it's doing is start to processing single job based on the priority. And processing single job, what it really do is going over the priority and trying to pop the job with the given priority. So if it succeed querying the job with the given priority, is then start processing it. And if the processing succeeded, then it exit. And it's starting again. So in practice, the threads will first try to eat all the threads with the first entry is the priority, and then move to the next one and next one and next one. This is the idea behind it. And I decided on multiple queues because I don't want to have too much contention when multiple workers utilizing the same queue to check if there is something to do there. So this is the idea, and everything is based on that. So we have this, and we have all the workers. And job itself is just the lambda, which is executed on it's took executed, and after that, we're moving to the next one. There is a lot like the code to do pass the instrumentation, profiler events, and stuff like that. And another thing that is Helpful there is the job handle. So as long as the job handle exists, as long as you have access to information if the job finished. And every job handle you can try to manually process. So you can just try to manually check if it's executed, and if it's not, you're just trying to process it. This is important because in some cases you're pushing something to the queue, so to the job system, and a moment later you need it to continue work. And you could wait for the job system to process it, but if the job system is very loaded, you can try to manually enforce execution of it. So this is something which is stealing. Some people call it stealing of the job, which is kind of nice features because it's help a lot. And of course, there is the job trigger, which is just the signaling that you can signal, so manually kind of mark it as finalize. So yeah, this is more or less kind of the system. If you have any questions, just drop the questions. I will be trying to answer them, but we'll just move forward to the next kind of topic. So let's return back to the presentation. Yeah. So the task system is not a perfect solution. It's a lot of problems there is with the mixing between the long task and the short task. I notice a lot of problems with that because some long task just taking too long, and because of that, if you have too many of them, you can lock the execution of the application. So you need to be careful about it. The dependencies is another things which can be sometimes tricky. And if you build the dependency tree in some weird way, there is possibility of the deadlock where if one task depending on another, in theory, is like it's a problem of the chicken and egg. It's hard to resolve, and we need to kind of to do something with it. And then finally, there are deadlocks that even if we're writing the job system, which can be perfectly safe, perfectly efficient, everything, there are still cases where we need to synchronize the data or access the data behind the logs. And in such a case, it's happened sadly that there are deadlocks. And you can resolve it some ways by not allowing that, but it still can happen. And finally, the problem that a lot of people have is like the problem if the task should be able to spawn another task. This is kind of I seen the implementation which disallow that. So you cannot create the task inside the task, which you can only create it up front. But this is a problem for tasks where the amount of the job that you want to spawn depending on the outcome of previous job, which it's different people approaching it in different way. There is I so far never seen like the perfect solution for that. And what I want to mention, another one, is the myths about atomics. It's like something that I've seen a lot of the people dealing with the task system and implementing it and doing the stuff even with simple multi-threading, thinking that atomics are cheap and atomics are solution for everything. They're saying that hey, let's use atomics. It's like it will resolve all the contention. There will be no locking. And there will be no deadlocks because there is the atomics. It's like atomics are not always the solution. And I've seen implementation of the atomic system, which would be slower than just using the right critical section or using the semaphores. The another thing is like there is the myth that, oh, but mutex is slow. So let's use atomics first and build whole system around the mutex. In reality, majority of the modern mutexes given by the sys operating system have already the first atomic section that trying first this quick access, and when it's fail to do that, then it's going into the full-blown mutex. So in fact, the mutex is a critical section in the first place. So there is a lot of these things that you need to understand the environment that you're working with. The another thing with the atomics is everybody who I know and they don't the atomic code, they are very kind of careful about the atomic code and they are scared of it. It's like the atomic code it's hard to test. It's like in simple cases, yes. In more complex one, it's terrible. It's hard to write a test. It's hard to resolve all the problems. You need to think about a lot of things. There is problem between the platforms that on some platforms you need to add some barriers that it work properly. On other, the barriers are put for you automatically. And people don't thinking about these problems. And I already encountered atomic systems that were so great that they were failing at just 2 threads. So just was enough 2 threads that the whole system go down in the right circumstances. So in this case, it was possible to write the test, but in others, even in my example of my system that I wrote, system can work perfectly fine for years. And somebody else with more powerful machine or having even some application running in the background, which changing the timing can trigger the fail. In this case, we noticed that running the Steam in the background was adding a lot of the instability there. So be careful when writing the task system, job system, and thinking that atomic system will resolve the problem with the deadlocks and using the critical sections. So this is kind of game over. No perfect solution for the multi-threading problems, and we can kind of go home. Is that right? It's not possible to resolve, so let's not do it. The thing about the system that we're creating is we don't need perfect solutions. We need just to have enough tools in our arsenal that we can use the tools that are there for the right things. So for example, you don't using the hammer to put the screw or fix the broken glass, right? Or not using the screwdriver to put the nail into the wall. This is the kind of the thing. And with programming, I believe it's very similar. We need systems and tools and understanding how to do stuff that they work. That's why another thing which I heard some people not even considering the parallel processing is that if you look into the definition of the parallel processing and focus on the word process, a mode of operation in which a process is split into parts. If we think about it in the narrow terms, like the process of the application, yeah, its application is a process, yeah. But if we search the definition of the process inside the dictionary, it's just a series of actions or steps taken in order to achieve a particular end. And I think this is the kind of the keyword of it, that it's very important that if we not focus so much onto just the computer, but thinking about it in the bigger scope, we can see some more possibility of doing stuff. It's not always, sometimes when you're approaching the problems, you need to approach it from different angle and look at it from different angles. And very often hard problem that you have becoming a lot simpler from another. In this case, if we know that this is just a process, why not to split it in multiple processes? So multiple application. And this is used by some people for a very simple use case like I will be discussing right now, which is the build system, where it's about the build system that we're using for the games, in this case for the games, but it can be used for anything. So we have the server, which communicating with the worker with the TCP IP, establishing the connection. And let's just focus for now on that. So we have the server with spawning the workers. I see very trivial implementation of that, where you're just spawning the worker, not even with TCP/IP, but spawning the worker with the specific arguments and waiting for the process to finish. And when the process finish, you're spawning another one, like another group of another ones, which is very inefficient because there is the cost of spawning the new process is a lot higher than the spawning the thread. The advantage of that is that if the process fail, for example, it's crash because, I don't know, the data is wrong or something, you don't need to worry about the crashing of the whole application, of the whole system. And with the connection of the TCP/IP, we can detect that TCP/IP failed without returning the proper result. And we can potentially restart the process again and see if it will succeed. If it succeeds, it's kind of okay, return the warning. Or we can, if it's failed, we returning just the error and marking that this data is invalid or there is some problem with it. The another problem of it, which we kind of can see here, are the DLLs on the side. I discovered that while building the system of the distributed system for the processing of the data, I ending with eating a lot of memory. So every type of the job that I want to process takes space. It's taking the memory. And I was putting inside the DLL so I can easily load every worker with the DLL that you can expand the pool of possible operation a lot more. So dropping the new DLL, it's picked up and it's just working. But every DLL was taking some memory and adding it up all into the memory for the workers. Turned out that the workers had like 250 or 500 megs of memory. You can work around this by splitting the job into the DLLs. First, parse the DLLs, read the information, what kind of the work they can execute, and just close the DLL. And later, depending on the works that is incoming, you're loading the right DLL and start to processing the data. The advantage of that is also that you can, in theory, fix the DLL, fix the issue in it, without reloading of the whole system. You just recompiling it, and it should be picked by the system. Another advantage of using the workers and this is also that you can potentially put some external compiler there. So you can spawn worker, process worker 1, which then spawning, for example, compilation of the shaders in the background, which is just another application. But you don't need to care about it. You can just put it, run it. If the external application crash or something goes wrong there is the external DLL. It's just, you don't care. It's failing the worker, which you can restart freely. And this is also the good thing because the external libraries, a lot of them have some problems. We encounter situation where the external libraries don't allow you for the multi-processing of the data. What is meaning that they have global state, which they shouldn't, and this global state stopping you from building the distributed solution because there can be only one instance. And for example, this is for logging. Or this is some global data that they're using to faster processing the data, the input data. So we encounter a situation like that. And because of that, this solution is also great, that distributing between a different process, because then it's easy to make the parallelization. You're just running different processes that loading the same library multiple times, different process, and we're running it and it's perfectly fine. We're just getting the results and it works. In the practice, we'll move back to the code. I will just move it here so I can see. In practice, this is also the system that is built into the engine that I work in my free time. If we look into the processes, my list of the processes that is running, here we have the resource center. As we can see, it's in the idle, it's using almost no CPU power. 2 processes, it can scale up depending on the requirement. So if there is more work, it can scale up to, if I could remember right now, 8 process, but you can specify by starting the application. And every process is around 90 megs. It may look like a lot, but sadly, this is the kind of just loading the DLLs and basic application taking a lot of space. And here is the icon. I can at any time quit the build system. So any application that's starting is connecting to this process and is able to start compiling. I also built the tooling around it, so to be able to understand what's happening inside it, I built the tool that connecting remotely to the process and extracting the data for this. So you can see here there is the there are two builders that you can see here. They are connected with the virtual file system. So file system is running like the file server, also the resource center, and is extracting the information here about it. And we can see here that these black things here is the compilation of the resources that happening there. So if I go, for example, to the test package, open, for example, textures and example SVG, I can go here and trigger a compilation of it for the stuff. And I have some dependencies here. In more complex case, I can go into the materials. So let's go into the system where I have some materials. Default materials, I will recompile it. It's over here. And we can see that there is the system. Everything is distributed here. So there is here a compilation, which is sadly this one is too small. So let's do it in bigger chunk to kind of show you. Recompile all platforms. Yeah. In practice, this computer is not perfect. And potentially, yeah. So you can see here, it's run in the parallel distributed compile all the resources that I triggered here. Not sure why there was the hang on the UI, but this is something that I need to check. And then you can see all the materials kind of information about the dependencies here that's happening. And error. This is kind of cool example also of the multiprocessing, that application crash. And as you can see, I can see that it's crashed, and also that it's crashed on condition front page is blocked. So I done something wrong with the memory, which is cool thing, because right now I can just go close it, go back, open once again the visual tooling, and I'm back in the game. In practice, this build server, how it works, it's once again, it has multiple platforms, but let's try to focus on the most important one. So the server is really distributing the task across different builders, and on top of that, taking care of the connecting, because everything worked through the TCP/IP in this case. We're opening the server, which start waiting for the incoming connection. We spawning the right amount of the builders. We can start builders here. We starting the builders with the right parameters, information where to connect to, and when it's connecting, we're getting the information. We're just waiting for the starting of the process and moving to the next one. This one potentially could be moved further to kind of speed it up, to start the processes and wait for the processes later. This is some optimization. There is a lot of it to do, but after starting, what it's doing is establishing the builder connection. This is still on the server side, which then have information about the connection and heartbeat. because we don't know if the system is still working, if the builder is still working or not. And depending on the workload, it can scale up or scale down the amount of the workers. With a minimal amount of the worker is always specified to some of these. Yeah, exactly. This is kind of the inspiration behind it. Yeah, this is perfect in the fact previous revision of the editor, I called it like a browser. It's like this is the something also pretty cool kind of about looking on the things on the broader kind of space scope, not only from one angle. When I started to writing the engine, I came to conclusion that game engines are very similar to the microkernels of the operating, like the Unix. So if you think about it, there is the memory management, there is the network management, there is devices, different kinds, there is the rendering, there is the file system. So in theory, all the systems, there is virtual file systems, which is everything that the microkernel had. A lot of people then, I had some discussion, a lot of people disagree with my opinion about it. But while I was working on the evolution of the UI here, I came to the conclusion that it's annoying that very often all the tools running in the same, we're paying the price for the tools that we don't use. Or one of my editor crashing and everything kind of falling apart. I'm not able to recover the work. And this is kind of the whole kind of idea that just like you, Philip told, it's like a browser. It's every tab is separate process. I want to push it further that you can have every process can have even multiple tabs. So what you're doing really, you're spawning the process, and it's connecting all the windows that it want to the main UI. This may be useful in some cases, but more or less yes. It's like that. The idea is that if anything crashing is done taking down the whole thing. From interesting thing, even the welcome screen that I'm using here is also a process, because I find out it's a lot easier for me to build it as the separate process, and potentially here I can later pull some information, state of the branch, and information like that, comparing to the building in the one application. This also added a lot of the cleanup of the code. This is the Qt combining with the Qt Advanced docking system. Yeah. And the Qt Advanced docking system is giving me possibility of doing that. So all this docking possibility and combination here is given to me by the extension for this. This is just separate library available on the GitHub. So I can dock it. Also the errors here is another docking kind of window. So you can see that where it's failed. Only window that right now is built in is options. And I know that for some people, the light skin is annoying, so you can switch it at any time. Sadly, I wasn't able to hook up it across everything. So it's not perfect, kind of. You can see even like it's using still the old icons, and they are missing some elements because it's written in the, is using the CSS styling for the windows, and there are missing some here. But yeah, so also things like that working across the different windows. So you see here is dark theme, and when I change to the bright one, it's changing everything else. It's because we'll have a chat about this a little bit later, kind of. Let's now focus on the build system, because this is the distributed application without the window. So yeah. So finally, when we spawn the worker, this is just like the container to manage the connection. Give me a second. Sorry for that. When we're connecting that, there is the builder nodes, and in the builder node is where the real magic happening. So in the builder node, there we have the part that I discussed, where we're loading the DLL, fetching the function. So we are able to load the external resource compiler, which is just one DLL. So if we open this, look at it from the perspective of the runtime, here we are. There is the tools, and inside the tools there is the plugins. And what it's doing, it's counting all the DLLs with the specific suffix. In this case, _R for the release. And it's finding all of these DLLs, opening them, and checking what is happening inside there. So what it's doing here, it's loading the library. Here is loading the information, and then unloading the stuff. And whenever we try to compile, whenever there is the work, here we're loading and fetching further, and there is the builder node, which is scanning the directory, registering all the compilers, and then forwarding the assertion further the pipeline. There is processing of the heartbeat when we try to unload. So what we're doing, we checking the DLLs. So every DLL we are loading after some time, because we don't want all the DLLs loaded all the time. Because as you can see, I just compile one of it. And whenever you're compiling one DLL, like the one type of the resources only, for example, working on the texture or meshes, you don't need to load all kind of the DLLs which taking the memory in your operating system. And you want your system as light as possible when it's running in the background. And yeah, so whenever you're asking for the resource task, you're getting the task, you're serializing it and requesting for the execution. Here is already processed, so here is sending for the execution. So it's trying to load it and starting the execution. So it's compiled here, deploying to the DLL, which loading and so on. A little bit of the magic there with the DLLs, because people that work with them know that they have their own problems. Like you need to share you don't sharing the memory. So when you're destroying in the DLL something which is passing from the main process, is becoming a problem. Another way around, the same. But it's possible to work around it by building the right systems. And yeah, whenever you finish, after that, you start processing the results, which you serialize, which in my case, I serialize the resource serialize the resource to the file and storing them into precompiled version. A lot to kind of fit into this. I once had the whole our presentation just about the resource system and kind of its evolution. So if somebody would be interested, I can try to kind of. I think you can even find it on the. It was on the Geek a few years ago. Yeah. And this is kind of more or less. There is just the workers, as we see that that there is the server to which you're connecting, and then the workers kind of try to do the work. And yeah, let's return back to the presentation. Yeah. Here we are, running a little bit late, but yeah. And finally, we're getting to the part which I see you are interested into, is distributed application. And how it works, as you can see, hub is the name of the main windows that you see there. The main windows is do nothing. Only its only purpose is loading the plugins and allowing them to hook it up to the whole system and register some services. And the services are just the pieces of the code that are running inside the hub, and they hooking up to the RPC system. So RPC can work to the TCP/IP. So whenever you're requesting the resource, any kind of the files or resources, everything go to the resource system, or they're going through the IPC, or some people know it as the pipe. So how it's do? I unify the system that it can work both of them. They have just the interfaces for the sockets, and you can have the TCP/IP socket or the IPC socket. And IPC stand for the inter-process communication in this case. So it's allowing just to communicate between the processes. This is something also which Chrome using. So Firefox Chromium tabs using to communicate with the main process also. And then whenever you're spawning the hub, you're spawning really the hub again, just with the in the client mode, and the client mode opening the DLL and start to processing the rest of the application through the DLL. And in the case of the world editor, I also loading the game DLL, which is the thing that processing all kinds of the game related stuff. And it's also responsible for 3D rendering. Then there is the DLL script editor, which could be visible for a moment there, and welcome screen. And all they do, they communicate, everything communicate only with the hub. As you can see, this is giving a little bit of the problem how to communicate between the processes, which in Chromium is not so important, but sadly in more complex application it's become. So for example, hub containing the settings setting service, and what it's doing is just holding all the settings that are there, and every client containing the setting client, which then whenever you're requesting the settings, it's asking the hub to retrieve these settings. Yeah, I think so. This is the one. Yeah. So this is kind of the more or less kind of overview of that one. And as you can see also on the picture above, the hub itself can spawn the resource center. And finally, let's jump the last time to the code base. And the part that I was discussing about the spawning of the multiple things, it will be visible here. So you can see cute stuff that is there, toolbox, everything. But let's move to the main that is there. So whenever you're starting working still sadly on it was ready at some point, but it's not anymore kind of working Linux implementation. And what it's doing is spawning the main application, which doing some initialization of the memory, initializing the memory system, and then base if there is the argument of the plugin DLL. If there is plugin, it's running in the client mode, and otherwise it's starting just the hub, which is part here. There is a little bit confusion here with the naming. Sadly, the hub and everything is the whole project have 20 years already, so there is some deprecated stuff and some things that need some love, but I'm working on it in my free time. Sadly, it's limited when you take into account that I have full-time job, trying to have normal life. I have family, so it's hard to find time to fix everything. And there is the client, which is what it's doing, is initializing the DLL and extracting from it appmine and just starting the tool interface there. And if we look into the hub, we can look also on the settings service that I mentioned. Whenever you're starting, it's registering the RPC. So you can see here, it's binding the RPC, which is the get string, for example, under the get string. This is a system wrote by me, so you're building the library with all of them, and then registering them inside the proper RPC. And that is communicating to the given system. And you have them. Thanks to that, you can have the common setting system. And then on the side of the client, whenever you're starting the client, you have simple interface, which is the global state, which is always the interface where I try to hide any kind of the implementation. And then inside, what you're doing, you're really calling the global system. So thanks to that, you always have all the settings are unified in between them. And because it's two-way communication, you could in theory here also connect some kind of the updates. So information that, for example, setting changed. This is work to do, but it will be kind of beneficial to have it, that you change some settings and automatically all of the clients are notified. And why stuff like that are important? Because I already experienced the system which they tried to build the distributed application, but what they don't really duplicate everything. So there was no common settings. So you could change setting in one window and it didn't affect the another, which is a problem. Yeah. So we have this setup. It's very important also to preserve the state across all the windows. Because otherwise you have this kind of issue that you change, for example, change the skin, and it's not applying to every window. It's just applying to some of it and some not, which requires some work. But in practice, I never regretted moving to this system. We have this one, and in practice. This is kind of what we have here. That is just the hub, which is the main system behind it. It have all kind of the services running. It have control over external windows. It have the build plugins that are supported. And in reality, this is how it works. It's working like that. It's allowing you to also a lot of flexibility. So, for example, I'm able to start the game here as the external application. You can see that it's loading, it's everything. And if we look into our tool, we can see that the LBA game is over here. We can see that it's loading the stuff. Most of them are precompiled, so there is no need for the resource system. We can run in the background. Here we have the game. It's running, everything is like that. Some could think that nice, but you want to have, while you're developing the things, you want to have to stuff inside the Windows. So let's start it here. Because why not? So if you build your application the right way, you are able to reuse exactly the same code to spawn the things. It's just, the difference is here I'm hooking up between the game windows into the widget inside the editor. It's here, and as you can see here, it's once again Little Big Adventure. The only problem here is because I still didn't hook up the inputs, which requiring some works. Yeah. Another big advantage of the distributed system like that is that sometimes, as you see, it's crashing and the whole application not going down, just going specific things of it. And you can have stuff like that you have the tooling, which you're only using Qt, using completely different library. And on top of that, I have completely different tool for the editor. So when you're starting the world editor to modify the things, this is kind of yeah, not a lot of happening, but I'm suspecting that, and you can load in the stuff in the background and in the same things, same time, everything kind of processing. And you see, everything is unified. The advantage of that is also that it's kind of, as you see, every process is there, and I can see that the world editor using a lot more CPU power comparing to every other editor. It should start loading here. You can see. So yeah, it will load at some point. Yeah, normally it's taking a little bit less time, but I'm also doing the modification, so I cannot really say that I'm surprised. But yeah, so this is kind of how the real example of the multiprocess application works. And this is also a way of the parallelization of the work. So you don't need to really build the whole application. Oh, here it is. And as you can see, it's loaded everything in the background. We can see how it looks. And it works. So yeah. Now it will probably crash. So let's return back to the presentation. So yeah. So finally, we're getting closer to the end. What about the coordinators? There are other ways of doing stuff. I would love to talk about the coroutines and other techniques, but sadly I never use them. And because of that, I don't feel qualified enough to have a discussion how they work and everything. So conclusion for me after writing this presentation was that first, multi-threading multi-process application is that multi-threading is easy to share data because it's one process. It's easy to implement because you can do it fast. It can't run, not necessarily work. There is lower performance overhead when you do it right. And memory overhead, of course, because you have one process. But comparing to the multi-process application, which have the better encapsulation, which meaning that the code, yeah, I'm also looking forward to this presentation of Philip, but the better encapsulation giving you better code, kind of. It's like things that every task is separate from the main process and it's not sharing anything. It's just kind of helping with doing the stuff. So because of that, it's make clean design. So when the visual scripting is there, it's only taking care of the visual scripting. You don't have access to anything else there except what you give it there, or will you communicate with the other process, which is a big thing, because in a lot of the bigger application, what I can see is very fast turning into the spaghetti code when people accessing one thing from everywhere because they can. Crash do not kill the whole application. In the multi-threading, sadly, crashes are common if it's done wrong. if write very often there is some, it's okay, but there is sometimes wrong data. Here, you're passing the data, you're processing it, it's perfectly fine. I also noticed that the multi-process application simplify debugging because you have one process which nothing happening there in the background. And in the case of the multi-threading, try to find the things into all these threads that's running, especially on more complex hardwares. And right now, some of them are like 24 threads, which is like the 24, like 12 cores, 24 threads, laptops, which is awesome. Just not when you need to debug and know which thread with which interacting and trying to find exactly which thread is the thread that doing what breaking for you. And it's also simplified testing, because if you wrote the encapsulated code, you wrote it in the way that you can execute it from another process. It's easy to start it, do some work, and check if this work is correct. And if not, you can also even write the test for this specific section. The cons of the multi-threading is hard to share data safely. And this is the problem of a lot of the multi-threaded code. And as I mentioned, the atomics are solution in some cases, but it's hard. Atomics are hard, and I prefer sometimes to avoid them because they hard to write, taking long time to do that. And even if you put a lot of effort into that, it's in a lot of cases they contain mistakes. And so far, talking with some people, the best way to even debug them is just piece of paper and trying to write down how they works. And complex for debugging, as I mentioned, multiple threads. It's hard to find it, especially when you don't know the system. And writing tests can be hard. In case of this atomic, which I mentioned before, we were able to write the test, but person that initially wrote the code told me that it's not possible to test it. And because it's multi-threaded, is happening in parallel, how I can know how to test it, how I can know how to force it to do the stuff that I want. And most of the time, the best way there is just to start bashing two threads together and just synchronize them to do that in a more controlled manner. But even that, sometimes it can run 100 times or million times and million one, some timing changing, and it's crashing or failing to do what it's supposed to do. The cons of the multi-process application, which is cons and also not in some ways, is requires thoughts about the communication. When you start writing the multi-process application, it's requiring a lot more planning, a lot more thinking how things should work. I notice personally that it's hard after years of the mindset of writing single application, of single process application, to start dealing with the application where, for example, to go for the options, you need to go to the external process, or to request the icons for something. You also need to do it, and it won't be right away. And of course, there is a memory and performance overhead. This is something that we need to always remember. It's not cheap to spawn another process. It's long time to spawn it. It's also higher memory overhead, because every process will have some memory overhead on top of it. And that's why the previous case, the simplest one, what I told you, that somebody wrote the spawning of the process with the command line, is a bad idea, because in this specific case, investigation discovered that we spent in some cases 80% of the time spawning the process and killing the process, and only 20% of the time working on the things that it's supposed to work. And it was running like it's 100 times. So in these 100 runs, 80% of it runs was really wasteful, which is also a problem for a lot of the multi-threaded things. And understanding it is like, is cutting the time of the execution is really better is really better. Because if I have one thread which running something in 1 second and two threads that's running it into the 0.8 second, it's like the time cost of the CPU is higher, where potentially you could spend it on something else. But from the perspective of processing, the processing is faster, 20%, which is can be small, can be large, depending on the situation. So you need to make decision if it's worth it or not, and really try to understand kind of the consequences of that, especially in the when you're writing just one system as the multi-threaded, which is part of the bigger multi-threaded system. Because especially in games, if you write something that is running 20% faster and you have resources for that, perfect. But if you don't have if there are other stuff running in the background and you're wasting using 160% of the core times of the cores, it's becoming a problem, and there is a lot of that. So my advice is that we don't need perfect solutions. There is no that end, there is no game over. There is just no perfect solution. We need to understand that. We need to think about it regarding everything what we works. There is this what we need. We are the solution that allow us to achieve our goals, and this is what we try to do. This is what we try to craft. If you can use the AI to achieve the goals that you want, go for it. But if the AI is not the thing and you want to use the Python because the Python is the best for you, and you think, should I use it because it's slow, because somebody is like millions of people using Python or Java or any other language, and it works for them in their use case. So there is no point to thinking what others saying that kind of is not optimal. It could be written better, because if it works in your use case, it will work. It's perfect solution kind of in some ways. And in my case, I decided to write a lot of the solution on my own, but it's mostly because I'm using my project as the playground. And that's why when writing the multi-threading, you don't need to write all of that. You don't need to think about all these systems. Sometimes it's just better to take the ready solution and just try to use it. Maybe it will be enough for you and you will be perfectly happy with it. With that and the tears of Olgerd, who is kind of appointed as the coroutine guy, we're moving to the questions, if we have any.
It was the hardest for you.
In this topic, to say the truth, the hardest was to understand with the atomics, for example, was to understand that I don't want to do atomics. It's like I experienced already with atomics things that I wrote the code, it works perfectly fine, and then I ran for it for a year. I shared my code with a friend, and my friend is like, it's crashing all the time. And he's like, what? You're doing it you're running it. It's like, it's work on my machine, right? Let's see what is there. And the worst part about it, I running the test then, and it started happening on my machine. It's like, but it's run before perfectly fine. And this is kind of the things. I think in the end is this challenging yourself that that what you know is not always what is there. And I also learn with this that I like to say that my code run. If it's working, I don't know. I try to verify it as much as I could, but I cannot give you the guarantee for it.
Are you using the shared memory with the multiprocess solution?
Sharing memory?
Shared memory, yeah.
Shared memory, I never use it. I know it's possible. Why I don't want to use it? Because shared memory is in some way hard to track, right? With the messages, if you have the build nice message system between the processes, in theory, it's very easy to see what's happening there. It's like you receive some block of the memory, there is and there is something wrong data there, or you parse it wrong. And I'm sharing right now it in the readable format of the XML. I know that not everybody like it, but I had a parser for it already done, so I'm using it. And it's just great. You opening, I had the situation where I screwed up some communication stuff, and it's like, why is it not working? I looking at the data that I'm receiving, and there is just garbage there. I know. With the shared memory, the problem would be that there is shared memory, is the pool of the memory, and you need to manage it on your own. And good luck with that one. If you go out of the sync, you starting corrupting the memory for every process, and you killing kind of the benefit of the multiprocessing.
I only bring it up as this might be kind of compromise between easiness of sharing memory in multi-threading and having a kind of safety with multiprocess, right? So you can somehow try to.
If you do it right, yeah, perfectly. It's like you can achieve it, but it's still easier to share it with the multi-threading, because in theory there you have already management of the memory on your own, and here you have this block of the memory.
Right.
Yeah, and also we need to remember that with the multiprocessing there is also this concept of the TCP/IP. I know there's a lot of people thinking about the TCP/IP as the slow network. They will try to use some kind of the IPC or the UDC, but the reality is that majority of the modern operating system internally replacing the local host TCP/IP as the IPC. So they're already doing the optimization for you. It's a lot faster than you doing it through the network. So there is a lot of these nuances that I think that what I learn and learning still is kind of the world changed. And I know that a lot of the knowledge in the internet is there, and a lot of the knowledge that you're learning about the C++ is kind of something that it's still valid, but it's not exactly how it was. Like with the not using the mutexes, because mutexes are slow, use critical section. Because in a lot of platforms, mutexes are critical section right now. Yeah. Well, you can shared memory. You can also share the memory in theory through the file by mapping the file system. So you can map file by multiple processes to the memory. This is also something that you can use. It's like in the older days, one of my friends was running out of on PS3 of the memory and was using, for example, this technique. So he was mapping the hard drive as the memory for the sounds. So you can do it right now also, kind of. I think that it's got even a lot better. So, but yeah.
Great. Any other questions? And in the meantime, I sent a link to the form, feedback form for Grzegorz. So if you can have some a couple of seconds, to be honest, because there's like 3 questions, pretty easy. Just to give some feedback to Grzegorz, I think Grzegorz will be happy.
Yeah, I'm open on always on the critique. It's like be free. If you didn't like it, just write you didn't like it. I would love to hear also even that why you didn't like it, or if you like it, just write why you like it. It's kind of in the programming you're learning that very easily to be kind of know to get the critique the right way. If you're not, you have hard time into the code reviews.
I don't see no more questions, so
yeah,
I think that's it. So thank you, Grzegorz, for finding time to share all your expertise and knowledge. I hope we will manage to make Olgert do another one.
I'm looking forward to that one.
Yeah,
but I know that the
happy.
keys are hard. So, oh, there is one.
Oh, hello, Slavik.
Yeah, hi. No.
I hope Olger is no for the team,
Me
not for
too.
the question from Slavomir. But yeah, I'm counting still on you about them.
Yeah,
Good
coroutines
presentation.
are a hard topic, as we discussed, kind of. The multi-threading generally is, and the deeper you're getting into the specific, is like you can talk about the task system, the 2 hours without any problem. So this is the kind of the problem. I wanted to focus here more on this multiprocessing and just show that the multiprocessing is also a way, which I know from friend that some don't believe into it. The GPU memory. Currently, the GPU memory, you should be I think you should be able to share it in some ways, because in the OpenGL, I'm assuming that potentially, I'm using the OpenGL, you can use the shared memory for the contexts. So you could spawn the context with shared memory, but only some of the things would be shared there. So I would say that this would be a way of doing that in this form. The sharing between the processes can be hard, yeah. Because right now what I'm doing, I would need to check the code to say the truth. What accepting the shared memory? If I could remember, it's accepting the other context. OpenGL. I need to check how I spawning
And there's a question if the code is available in public.
The code, sadly not. It's like it's still work in progress. There is currently there is more than you could kind of see. It's like there is the whole virtual file system. There is memory management. Like currently to some, I simplified it because I wanted, but it's not available. I consider that at some point, but also I working with companies, and I work for Unity for 7 years, so it's kind of the conflict of the interest if I start publishing sharing the code for the whole game tech stack, because I wouldn't call it only the engine. It's the editor, it's the tooling, I want to create the whole pipeline of building the game from the beginning to the end, even to the stuff like you pressing the build and it's building you the final package for the game. And it's proving to be difficult, to say the truth. It's like there are a lot of this low-level stuff that you need to deal with. Is like even with the multiprocessing, something that I didn't mention is when you're doing the queued, you need to start to sharing the window between the two processes. So you're returning the Windows handle from the sub-process to the main process, which then you injecting into the window. And the problem with that is that at that moment when you're doing that, and the queued in practice start to sharing in some ways the process, like the event queue. So what's happening, if you only updating one of the event queue and not the other, at some point the event queue will stop updating. You need to do update on the main process, so it start to processing. And if you are unlucky and you have the timing wrong, you're getting very laggy application. It's like it was surprise for me, and I needed to change it the way how I injecting the custom events into the whole event pool, because the moment when I try to process a little bit of the events, do something at the process, it was enough for me to kill the performance to the way that if I drag the mouse across the in the welcome screen across the buttons, it was visible delay between the lighting up the buttons. And this is one of the problems. Another one of the problems is that in this case I still kind of don't know what is the problem there, to say the truth, is that whenever you're dragging the mouse, you need to send the event to the DLL that the mouse movement happened. And there is some delay between the movement of the mouse and the processing of the events. And I still don't have idea what's happening there on this communication level. So the communication there is this. And there are problems like that, yeah. I could talk about the problems for a long time, because this is kind of what you do. It's like when you go into the work and you start working in like the companies like Unity or Ubisoft or anywhere, you start seeing this ready system, and you're saying, yeah, oh, it's work like shit. It's like, there is this code which is, you don't know why it is there. And then you start to write application after 20 years, you think, oh, why the fuck is this code there? And it's like, oh, of course I wrote it. It's like it's there because of some reason. Yeah. And you start seeing this very similarity in the work when you're sitting in front of the code there, which have 20 years, and magically, oh, I know this code. I wrote something similar in mine at some point. It's like, this is how it is. And also because of that, it's like I cannot share it right now because it's a year after I left the Unity, but I'm considering kind of at some point sharing it. There is, I think, a lot of place that people could help, because it's like, you cannot do everything alone. Like, I have a friend helping me a little bit with it, but this is kind of how it is. Yeah. Yeah, this is kind of where I also kind of think about it. And there are some problems which is interesting for me because Philip mentioned that this looks like works like the Chrome browser, and this is also the problems that the Chrome browser also have in some ways. It's like this is, for example, you can start the world editor here, so the world, and then you can start the embedded visual scripting, because you have the embedded script inside the world, and it's kind of the visual scripting is connected to the world. It's not part of it as the editor itself, but the data coming from it, and how to give the people input that this is part of the same world, or there is connection between them. Or even the thing that if you have the multiple windows running at the same time, you want to have the visual scripting and the world editor at the same time on the screen. How you kind of notify about it the users? There is a lot of this problem, like the split screen for the browsers, not two windows, just the split screen in one window, where you have one web page here and one web page here, and you manage them as one window. Things like that are still unresolved in the even the browser environment when they're using this multiprocessing. So there is, I agree that there is this value of learning there, and I think that it could be also beneficial for me in some ways, because people looking at the code potentially can also find flaws in the code, which is errors, or find some better ways, offer other better solutions for it, because it's the problem also with doing the project in free time. You very often like talk with the Olgert. It's like, I don't multi-threading, the job system and everything, and he mentioned that there is better solution for that. And it's happening all the time, that you kind of, even with your old kind of wrote something, and 2 years later you're looking at the code and it's like, who wrote this? Oh, it's my code. It's always my code. Yeah. So this is kind of how it is. And this 20 years, it's teaching kind of this humbleness in some ways, that if you see some bad code that is there in the code base, often you need to more know about it, if this is because, for example, they were in a rush, or this was just the way to make it work in the environment that they had. Because this is something that I also need to do, is like, there are some sacrifices that I need to do to make things work in this environment. Yeah, I was checking this multi-threading. Execute resources. Render thread.
Okay, guys. Last chance of asking question.
Yeah. So in theory, what you're doing, you're passing the GL context to the make current when you're spawning the shared context. So I think it should be possible to, at least in OpenGL, to share the memory. So this is I'm using SDL underneath for the things. So it's in theory you're setting the root context and then you're selecting the. This is the structure. Here is initialization. I think this is the same. Make current.
Okay, show your code editor.
Yeah, you can. No worries. There is no. Oh, there is GL share. Yeah. So this, I think it should be possible to kind of with current context. So in theory, if you can share the contexts between the two processes, I think you should be able to share it. And internally, if I could remember, it was passing the shared context. So there is a lot of this code kind of. It's like the whole structure is like that right now. So there is around 500,000 line of codes here.
Nice.
Yeah.
Sławomir is happy. At least.
Yep.
So
yeah.
okay.
Some car.
Okay, guys. So thank you, and
Yep.
Gregor, thank you once again for taking the challenge.
I want to believe that you guys had and girls had fans here, kind of looking at this stuff.
Yeah. I think that was very valuable presentation. So thank you once again for doing it.
Yeah. It's like
I'm keeping finger crossed for the Olgert.
Yeah. Me too.
Yeah. And I wish you a good evening.
Have a good evening, everyone.
Thank you, guys.
Yep.
Bye.
See you.